Hello, everyone. How are we doing today? It is Friday. Remember to silence my phone here. All right. So, I I imagine that you all probably get these notifications too if you're signed up for the university stuff. The it it gives me a bit of a chuckle that they've changed to sending out the notifications for the parking lot closures for basketball the day before, and not sending another reminder the next day. Like, why wouldn't you send one both days? Just feels like, huh? Uh, it well, no, and this is a bit cynical of me, but it seems to be like a setting up for failure sort of deal, because you're gonna have a bunch of people forget, and that's expensive. I haven't I haven't had the misfortune of getting a parking ticket here on campus for quite some time, but when I was an undergraduate, I got one, and looked like the paper tickets that they handed out at the time had like a list of all the costs for the different infractions, and they just like check marked the box. And um, at that time, at least, it would have been cheaper for me to park in the grass somewhere than it was for me to have parked in a faculty parking spot, which was pretty silly in my eyes. Okay, there's a question in the chat that I will see if I can get to the relevant information here quickly to be able to sort that out. Asking about a link to computer graphing software. Hold on. Ah, okay. All right. That is because I forgot to update the table of contents or something. Okay. So, thank you for the reminder. There's been some stuff that I've been writing up in the background, and that I need to get posted later this afternoon with the quiz. Since we're getting up at the close to the end of the semester and Thanksgiving break is going to interfere with things, um, I'm probably going to end up pushing back the due date for the quizzes uh, for some stuff. And this week's quiz will be for that because I've been trying to finish writing up the online notes for the early chapters in chapter 16, and there are a couple of links and uh, things that I have embedded in those notes. Part of the reason it's taken so long is getting all the images and stuff made. This is this is one of those chapters that's got a bunch of pictures in it, and graphing 3D stuff is way harder than graphing 2D stuff. So anyway, I'll catch up on that and then post those resources later on, along with the quizzes for the last couple sections we covered, and adjust some due dates. You'll have plenty of time to catch up on the last couple weeks of things. Uh, so I believe the current quiz is quiz 10, and when I get into Blackboard, I will push that back. If I happen to forget to do it this afternoon, don't fret about the due date. It'll be sometime next week. All right. Alrighty. We need to talk about parametric surfaces. For parametric surfaces, the idea is basically a two-dimensional version of what we had for space curves. So we're going to have, instead of what we saw for space curves, where we we would have some function that was defined like so. We think about t, of course, in some interval. For a parametric surface, we want to define a surface. Their book uses the variable r as the parametric function. And now our location functions x, y, and z are all given as functions of two variables. Okay. Where, of course, now we think about the ordered pair UV being in some domain D that is a subset of R2. Okay. From here, there are essentially two elements to what it is we need to talk about. Number one, we need to familiarize ourselves with examples of surfaces in this context, get used to parameterizing with respect to two variables, and then also to recover some of our information about how calculus is performed on these types of objects. Okay. So if we have a parametrics equation looks like this. We're not given any specific restrictions on U and V. So the assumption is that they are points in R2 that work, that obey the equations, right? And so the idea here is that we start examining what's going on with our equations here to figure out what information can be extracted. Okay, what relationships, if any, exist. Okay, should be pretty clear for us. That if we take x squared plus z squared, we're going to get this. Okay, and so this tells us that these two things sit on a circle, right? Okay, and because this here is just a free parameter, right? There's no restrictions on V, It doesn't do anything. It's just allowed to assume all possible values. That our shape here is a cylinder of radius 2 that points in that direction, right? Centered at the origin. Okay, so relatively simple there. All right, sorry about that. The masks and microphone make taking a sip of something a production. Anyway, so we can talk about other examples too. Another one that your book does that I think is interesting that we'll discuss. But without breaking out some serious hardware, can probably not replicate. Okay, so here we have this shape here, and the instructions for the textbook on this example tell you to use a computer algebra system or something. Okay, use technology in order to make a plot of this shape. Okay, so the idea would be to figure out what's going on with u and v so that we can come up with some idea of what this is going to look like, right? So these terms here, if we're thinking about what they do, we know that sine ranges from -1 to 1, right? And because sine ranges from -1 to 1, that means that these things are going to range from 1 to 3 in terms of the value of the number that sits there, right? That's how that's going to go. Okay. And the value for these numbers are linked. Okay. So they're always the same at a particular point. And we know that cosine and sine, when taken together, are going to give us, with respect to the parameter, a circular shape, right? So what I have is a circle with a radius that is changing based on the value of v. Okay? And then this part right here is, as u increases, this value goes up, and then cosine v also ranges from -1 to 1. So it's going to add some wobbliness to it. with respect to the v parameter, right? Okay. Now, I'll draw the shape here in a second, but before I draw the shape, I want to give an impression of how we think about the parameterization of the surface itself. We have some domain, okay? And in this domain, we think about it being broken up into the u and the v directions, okay? And for the sake of things making sense, we imagine that u and v as directions are orthogonal to one another on this 2D surface, just to make things as simple as possible, okay? Now, on this parametric surface, I can think about a line where one of these parameters is held constant as being a curve C1 or C2, right? So on this line here, there's a value of v that's being held constant, right? If v is the vertical, I'll make that more clear. Okay? Here, the value u is being held constant. And if we translate this to what this may look like in a 3D, I'm a terrible artist, so what would happen is those two curves would sit on this surface, where you would have C1 here and C2 there. Okay? So imagine having this domain D, okay, and using this formula or some other formula, whatever it happens to be, as instructions to how the surface should be deformed to make a 3D shape, right? So this would be like a flat, thin piece of clay or something, right? And then what you do is use these as instructions to tell you where every point on that clay should end up as you twist it, stretch it, and bend it around in order to make it into whatever surface it's supposed to look like. Okay? And if you do that by imagining this thing being deformed, these lines get mapped to curves on that surface. Okay? I'm sure at least some of you have done the thing where you take Play-Doh and like mash it on a newspaper or something to take an impression of the ink and then start pulling on the Play-Doh to stretch out the picture or the words in the newspaper or whatever. It's the same kind of deal, right? It's a continuous process. Any straight lines would be deformed based on what manipulations you make to the Play-Doh. All right? So the example that we have here, drawing the picture is kind of a doozy. Because what we end up with surface-wise is this spiral shape. This is in your textbook. Okay, I'm not going to be able to do any better than that when it comes to drawing it. All right, but you have this cylinder basically that is deformed into a helix shape. Okay, so I don't know. You may have had straws or something as a child that vaguely resembled what we have here. Okay, but this is not the kind of thing that we would expect you to draw by hand. All right, we'll want to use computers for this, but the issue with the parametric surface is that unless you have specialized computer tools, which get to kind of the edge of the things that might be freely available or easy enough to use online, that they don't require tons and tons of practice, that we have to be a little bit careful, right? We need a whole day talking about how to program up stuff in Python or MATLAB or what have you to be able to accurately recreate this kind of surface, or show the kinds of cheats that are used in order to figure things out, right? So like one of the things that we could do is do like one small slice of this, right? So instead of taking the whole cylinder, I imagine the cylinder as being broken up into really thin strips. And then I plot one of the strips at a time and construct the whole thing. All right, so each strip would be like a thin little rectangular helix thing. And then I put them together by breaking it up in enough small pieces. Some of the pictures that you may have seen in the older notes had to be done that way, right? When I was making cylinders, you can see small little divisions in them in order to get the 3D shading to not look terrible. All right. There are some things that are really nice to have parametric equations for, such as the parametric equation for a plane. So if I have some point and I want the point and two distinct vectors A and B to be in the plane, if P0 is given by some value R of T naught, which we can call just R sub 0 here, then what we can do is we can say the equation of a plane where I could end up at any point here, right? Should be able to be expressed as a vector where I start off at P naught I'm trying to be careful about how I draw this. I almost got the right height. Shorter. Okay, sorry. Trying to make those parallel to A and B. So there's U times B, or sorry, v times b and u times a, right? And I can use those two vectors in a linear combination to traverse the space. Does that make sense? So I travel a distance u in the a direction and then a distance v in the b direction. Okay. We see that it forms a parallelogram, which of course is how vector addition works, right? I can add in any order, everything's fine. So parametric equations for planes are quite simple. We're happy to see them. Okay. Should also be no surprise that we have parametric equation for a sphere of radius r. Okay. And obviously these expressions are not unique, right? I could describe this plane some other way, right? Or reverse the meanings of it. A and B, or switch U and V around, I still get a parametric equation. So the parametric equation, there are going to be multiple ways to express the parametric equation for the sphere as well, right? So if we make a quick sketch of some sphere, okay, looks like so. The most sensible way to think about this, of course, is the one that corresponds to our knowledge of spherical coordinates. That should be a way to parameterize a sphere, right? Using our azimuth and polar angle in order to figure things out. And so we need to make sure that all gets set up correctly. So one of the things that we could say is we could set x equal to r times sine phi cosine theta, y equals r sine phi sine theta. Z is going to be equal to r cosine phi. Okay, where phi is the polar angle in this case, and theta is the azimuth. Okay, but this isn't the only way that we could have written this down. In order to be able to give us the ability to navigate to any point on the sphere. There's nothing wrong with switching sine and cosine here or something, right? As long as I can get to everywhere on the sphere, that would just be a rotation of the sphere in some sense. Okay? or as we discussed quite a bit when we were talking about spherical coordinates in the first place, we can reverse the role of theta and phi in this explanation. That would technically be a different parameterization. So, different ways to think about that. Parameterizations in general can be thought of, by the way, in terms of coordinate changes. Okay, that's essentially what it is, right? A parameter or change in parameterization is a change in the coordinate representation of something in some sense. We have to be a little bit more careful if we're talking about this from a linear algebra perspective, but this is not quite linear algebra. Okay. All right. I do want to, at this point, as I'm about to get into the more technical examples for the section, this section is long in your textbook. It's mostly because there's lots of examples. I can't show and quickly reproduce all the examples or equivalent examples that show up in the text. So please make sure you read through those. Okay. Sorry, another drink break. For tangent planes, because we also need to make sure that we are discussing the calculus concepts that are associated with these ideas. I had mentioned earlier that we could have some kind of parametric surface. And if I flatten that surface out, let's redraw the whole thing, I guess. Okay. So in the 2D shape, we would have lines that would look like this, right? We would have a C1 and a C2. And after being deformed on the surface itself, it would look something like this. Okay? So that's what's going on. And if we have our parametric surface that is given to us by a standard set of equations here, what we're interested in is what happens as we travel along one of these curves in or along the surface. Okay? Because if I'm sitting here at some point that is given to me by UV, movement in this direction would be movement in the u direction, and movement in this direction would be movement in the v direction, right? Because we think about this as the uv axis within the domain, okay? Ultimately, what I want to do is to be able to talk about the tangent plane at a point uv, okay? To be able to set that up, what I need are these vectors, the tangent vectors to each of those lines, C1 and C2. Because if I have those tangent vectors, I can take their cross products and get a normal vector and have the normal vector to the plane and use that to define the plane. Okay, so that's what we're setting up here. The idea is that we take, sorry, I wrote the wrong letter, the partial derivative with respect to u of this expression in order to get one of those vectors. And the partial derivative with respect to v to get the other one. I am, for completeness' sake, going to write this using both kinds of notation. Obviously, one of them is a little bit less writing than the other one. Okay. But we get these values. Now, if we're talking about the tangent plane at a point, we of course do these evaluations at some specific u naught v naught. Okay, but it's tedious to write the formulas that way and get everything set up because you can compute the formula in general and then plug in the values, right? Because that's the way that you would need to do the computation. So if we want to build our tangent plane, let's talk about an example here. So we are given the parametric equations for this surface. X equals u squared, y equals v squared, and z equals u plus 2v. And we are told that we want to find this tangent plane at 113. Okay, now, just so it's said, that's an XYZ point, right? So we'll have to figure out the appropriate u values in order to make that true. pretty clearly the case that u equals 1 and v equals 1 are the answer there. Okay, but you do have to resolve that. Okay. Now what we want to do is we want to write what, keep writing r of x, r of u, and r of v are in order to get these things set up. So we take the first partial with respect to u, u squared differentiated by u is 2u, v squared differentiated by u is 0, and u plus 2v differentiated by u is 1. Do the same thing with v. Differentiating polynomials is still easy, so we get relatively simple expressions here. Okay. Now the next step in this process is, as I mentioned, we need to take the cross product of these two vectors in order to get everything together here. Okay. The other thing that we can do, because we're down to the cross product type computation, is we could, if we wanted to, take the cross product and leave in the u's and v's, right? And that would give us the normal vector at any point on the surface as a function of u and v. The other thing that we can do is we can plug in u and v right now and then just take the cross product of the two vectors individually. Okay. This is easy enough that we don't need to plug in stuff beforehand, but if it looks bad and you only need the tangent point or the tangent plane at one point, you can plug in the numbers before you take this cross product. Normally, you don't ever want to plug in the parameter values until the very, very end, but this is a situation where if you only need the tangent plane at one point, you can get away with it. All right, so we want this cross product. We use our heuristic notation for this. Keep things easy. Okay. So we're going to end up with negative 2vi minus 4uvj, sorry, excuse me, 4u minus, sorry, just 4uj, excuse me, and then plus 4uvk. All right, so we can simplify this slightly. Resolving the minus signs. Okay. And then we can plug in u and v are equal to 1 in order to get our normal vector. I'll write that as n. So that it looks like this. Okay. And then this tells us that the equation of the tangent plane at 1, 1, 3 with this normal vector, looks like so. And we can multiply everything out, do a little bit of arithmetic, and then see that this is what we get here. Okay, so not so bad, right? Mostly tedious. Okay, it's not hard. There's just, we have to remember where all the pieces go. If you're given a parametric or vector equation, if you're giving parametric equations or vector equations for a surface, and you want to find the tangent plane at a point, you need to, of course, know the point, compute the partial derivatives with respect to the parameters, which will give you two vector functions, and you take the cross product of those two vectors in order to get the normal vector on the surface at some point u naught v naught. You plug in the particular u naught v naught that you're interested in, and then use the point on the plane with that normal vector to write all this out. Yeah? Okay. Okie dokie. This is a long section. Okay. There's one thing we didn't quite have time to get to today, so I want to mention it, even though we're not going to have time to do a full example. But if we have a parametric equation, we can talk about surface area. Okay? And the idea is that if we have a parametric equation in the format that we've had for this whole section, I want to talk about the area of a surface. I can find that by integrating the magnitude of the normal vector over the area. Okay? So what happens is because this is a magnitude, this is always going to be a scalar function, right? It's always going to be just a function of u and v after I do all of the necessary algebra. Okay? Excuse me. Okay? So, one version of the problem involves just writing this out, setting up the integral, and then going from there, right? Okay. Now, there's a second version of this that is what happens when we can think of the surface area as being some graph, right? So if we have the normal situation where we have x and y in some domain and some z, and then we have a surface floating in space, and we want this surface area. So we have this parameterization. This is the standard parameterization, but it's a valid parameterization. Yeah. We can still use this equation in order to set things up. Okay. Except it's going to turn out to have a convenient form that will resemble arc length and surface area from what you're used to seeing. It looks like so, right? Where we do the normal sort of thing where we write this in differential form. We take the derivative with respect to x and y of z, so we get dz dx and dz dy, right? Or partial z, partial y, and partial z, partial x in this instance. And then I can factor out the partial z, partial y. They end up here, right? And then I just absorb that into the dA like we did with the dt's and dy's and dx's and stuff back in Calc 2. Okay? But this thing in this form just looks like a 2D integral. Okay, after you take the partial derivatives, because there won't be any z's left after you compute these quantities. All right? So take a look at that. I apologize for stealing a couple of minutes here. I hope everyone has a great weekend, and I will see you next time.